Welcome to the afternoon keynote talk. So I'm very glad to introduce Professor Nathan Lazarus from University of Delaware. So I know Nathan for years. He graduated from College Mellon, getting his PhD, and then in 2012, and then he went to the U.S. Army Research Lab (ARL) to do his independent research over there. And then he had done a lot of the stretchable electromagnetic devices for soft robots. And today he will give us his like research accomplishments and research talk on this topic. Before I goes into his talk, I would like to mention several awards he received, and then some of them are amazing. So he get the ARL Earlier Career Award, and then he also get the ARL Honorable Award for Engineering and the Rookie of the Year in 2016. And then the most important one, he get the PCAS awards, which is the highest honor for the U.S. government for the research in the early career. So this is my pleasure to introduce Nathan and his research to you. So I will leave the stage to him. Thank you.
Thanks for the kind introduction, as well as the invitation to speak today. So as Po-Yen mentioned, I'm going to be talking about my work on soft and stretchable electromagnetics. And like Po-Yen, I also was inspired early in my career as a young postdoc by Dr. Dickey. And so you will see a lot of liquid metal over the next few slides. I do work much more at the device and application side, so showing a lot of how a lot of these devices can be applied to soft robotic systems. And I do collaborate with Dr. Dickey, although I don't think he's on this particular kind of project area. So we've introduced it several times over the course of the morning, but I want to again kind of reintroduce this idea of soft robotics, that conventional robotics basically very, very powerful, but because they are so powerful, they also struggle around fragile objects, struggle around human teammates. And so this area of soft robotics, trying to take low modulus materials, plastics, elastomers like silicone, using those materials to bring robots from the factory floor to the community with numerous applications. I think we've seen medicine, there's agriculture, consumer products, as well as defense. With a lot of the ability to softly grasp and conform around fragile objects, very similar to our own hands, very similar to many biological systems. But the dirty secret in soft robotics, and something that's come up several times this morning as well, is that the reality is, in most cases, these soft systems, there's actually a sizable pump just off screen, pump, a motor, something like that. And this is very different from a lot of the biological inspirations. Something like the octopus is almost entirely soft, with the exception of its beak. And so an octopus a foot or more in size can fit through a hole the size of a quarter. And so if we can make a fully soft and untethered robot, we'd be able to enter deep into areas like caves or buildings. We'd be able to basically, for use in things like search and rescue, reconnaissance, and so on and so forth. However, because of this reliance on pneumatics, this reliance on balloon type structures, there's basically a very strong tendency to have embedded robotics or embedded pumps, embedded motors within these otherwise soft structures. And the only really alternative to this right now is these more unconventional approaches, things like the fluidic driven techniques that Ryan was talking about earlier today. Within more conventional robotics, electromagnetics is really the dominant and most widely used approach. We see it in a wide variety of pumps, we see it in valves, we see it in motors, among other things. And the reason for this is that you can have easy electrical control, you can generate large forces, and you can basically get a fairly nice linear response with current. And so that's why it's been such a widespread technology. Where soft robotics, instead, we're basically dominated by pneumatic actuation. And so somewhere in the system, you have a rigid and heavy electromagnetic pump. And there have been a limited amount of work in stretchable electromagnetics, but they're relatively rare and relatively primitive. And I'll talk a little bit the next few slides on the reasons why for this, but I believe this really is the most promising path toward a fully soft, electrically controlled, untethered robot. So a robot that would allow us to use the techniques that we've developed over so many years in conventional robotics and apply it to the soft robotics space. So in my talk today, I'm basically going to be focusing very heavily on the electromagnet. So the electromagnet or inductor, which is really the fundamental electromagnetic passive. The disadvantage in a lot of electromagnetic design is that most of the features that make an inductor or an electromagnet good, such as using many, many turns of copper wiring, using rigid ceramic magnetic materials, also make it a very rigid structure. So I'm going to begin by talking about materials for stretchable electromagnetics, liquid metals like Dr. Dickey, other different materials that we've been working on, and then talk about some more soft robotic application examples with the main emphasis trying to find ways to use these stretchable electromagnetics to basically move fluid within a soft robotic structure. So making soft pumps, making soft actuators to drive a soft robot in a more fully soft, stretchable system. And in order to do this, a lot of my own background, a lot of the work that I started in my career was in an area known as stretchable electronics. So basically, I did much of my early career in an area of basically wearable wireless power, trying to make wearable sensors and basically that can match very closely the behavior of the human body. So basically think of sensors and electronics that can match the performance of human skin. And we had to get away from conventional materials and basically shifting toward highly deformable systems based on things like silicone and polyurethane. However, in doing this, we basically had to rely on new materials, new designs to allow us to gain stretchability, allow us to gain softness, to survive significant strains without permanent damage. And the disadvantage of doing this is that in some cases, we inevitably end up with a certain degree of loss in performance. So in order to gain stretchability, we give up some degree of electrical performance. And a lot of our goal as designers and engineers is to minimize this loss to achieve performance close to more traditional designs. Now, to make a stretchable electromagnet, to make a stretchable inductor, fundamentally, these devices are a coil of wire. And so as long as we can make the wire, the conductor itself stretchable, we can potentially make an inductor coil. And there's three main approaches that the community uses to make stretchable conductors, each of which have advantages and disadvantages. One of the more classic ones is to stir conductive particulate into an elastomeric material, which is very effective, but also has a relatively low conductivity. So something like many orders of magnitude lower than a traditional conductor like copper or silver. Alternatively, we can take a traditional conductor and add serpentines, basically make something more like an accordion, something that can kind of stretch and fold to give us some degree of stress relief and allow stretchability. Stress relief structures have the advantage of being good conductors, traditional metal materials, but limited typically in their maximum stretchability. That you're typically not going to see 300, 400, 500%, the sorts of things that the liquid metals can do. You're more talking the 20, 30, 40% that you need for most of the human body. Trying to make high performance conductors that can do the types of levels of deformation in soft robotics, pretty much you have to rely on these more unconventional approaches like room temperature liquid metals. So we need a balance between high conductivity and a very large ability to survive mechanical strain. And I'm not going to, Dr. Dickey did a wonderful job of introducing it this morning, so I'm not going to go into detail on the material, but one of my main conductors of choice, again, is these room temperature liquid metals, which have some very large advantages from the perspective of making current carrying devices. They're able to flow to match a surrounding elastomer, and so you can get very, very large deformations. You can get hundreds of percent strain, and you can do it even for large cross-sectional areas of traces. Because these larger cross-sections are the only real way we have to compensate for the lower conductivity in the material. A lot of my own work's using another liquid metal called Galinstan, very similar to the eutectic gallium indium this morning, very similar in properties and so on. But this is a eutectic alloy or eutectic combination of gallium, indium, and tin. And it again forms this thin native oxide, which has a number of advantages in it. For the perspective of a lot of devices we're working with here, the main one is that once they're in place, they don't easily leak out of the material. You have to apply an active pressure to push them out of a channel. And they also can be considered in some cases self-healing for that reason. Now, for making a stretchable electromagnet, this gives us some very clear advantages. That the first, again, is you can make nice thick traces, you can minimize the resistance because they're still stretchable at larger cross sections. You can also use very conventional designs, so parallel straight traces that are difficult to make in some of these other types of geometries. And so we've shown the ability to stretch by hundreds of percent without damage. We've looked at a wide variety of different designs, planar coils, solenoids, and so on. And so this is a very well-tested approach for making soft coils for sensing and wireless power transfer. But one of the challenges, particularly as you start getting into actuation, is that basically now we're talking putting very significant levels of current. The traditional uses of these types of devices, you might be trying to get milliwatts of power onto the body through wireless power to charge a device, charge a wearable battery. When you're talking something like electromagnet, you might want to put 2 amps, 5 amps, some very, very large current levels. And so we did one of the first study to basically put very substantial currents through these devices to try to find whether they ultimately are stable enough to make reliable electromagnetic actuators. And we found that that importantly, even for some pretty substantial currents, so up to about 10 millimeter or amps per millimeter squared, we could get indefinite survival in environment as long as there was some degree of temperature control. It does at some point eventually start seeing some failure mechanisms. Eventually you get electromigration. So basically the redistribution of liquid metal due to the current flowing through at the days to weeks time scale. And if you go to even higher levels, you basically get direct thermal failure. So the expansion of the surrounding silicone and then basically pinching out regions of the liquid metal. But importantly for our purposes today, the fact that we're able to survive very high currents, this is a very promising path toward creating a fully stretchable electromagnet. Okay. So the second material set that we're looking at is that electromagnets typically include a magnetic material to try to guide the field lines and kind of get the field where you'd like it to go. However, traditional magnetic materials, the irons, the ferrites, these types of materials are basically very, very rigid and not at all well suited for soft robotics. And the traditional soft robotic materials are these elastomeric polymers, silicone, polyurethane, that are not intrinsically magnetic. And so one of the areas that we worked very heavily in was trying to develop soft and smart materials that are rapidly responsive to electromagnetic fields. And we'll talk about a number of these areas in the next few slides, but we've looked at composites, magnetic fabrics, magnetic suspensions, and foams. And the main driver of a lot of this work was, again, more for wireless power systems. So making a stretchable magnetic backplane to couple energy for improved power coupling. However, they turn out to be very promising for soft robotic applications as well, due to the ease of electrical control and tunability of the behavior. So the first of the magnetic materials that we looked at was something called a ferroelastomer. And this is a relatively simple material. Just think of taking something like silicone and just stirring in magnetic particulate. And we looked at a few different types of particles, but the one on the left is something called polypermalloy powder, which is, in this case, was about 30 micron spherical particles within the silicone. The one on the right, more of a flake type geometry, to basically, I think like about 100 micron platelets of another high permeability material known as sendust. And both of these just stirred into the soft silicone EcoFlex 0030. And we wanted to understand what are the resulting magnetic properties. And in this case, because we are just stirring them randomly into the material, we don't have a definite idea of exactly where each particle is found. And so the way that we modeled this, or the way that we kind of understood this, was to apply something called effective medium theory, where we basically are trying to estimate what the overall material, the overall behavior of the composite is, by looking at making certain assumptions about the distribution of the particulate. And in this particular case, we have roughly ellipsoidal particulate. We're assuming we've mixed them fairly evenly within the composite, and we're assuming that by magnetic standards, there's a relatively low density. And so we want the mechanical performance to remain dominated by the silicone elastomer. And so we can assume that they're weakly interacting. In this particular situation, the dominant, or the appropriate model for this is something called the Maxwell-Garnett model. And we found that our behavior matched the expected behavior very closely, both for the more spherical particulate, so the polypermalloy powder, as well as for the more platelet geometry. We found that it matched what you would expect for a fairly random orientation of these platelet materials, as we'd expect from randomly stirring it into the material. Now, another concern at the time was that we're using powders with two different materials of two different shapes due to what I could obtain commercially at the time. And they are both high permeability. They're both low loss materials common in a technology known as powder core inductors, where you're basically trying to pack a very, very high density of particles into an inductor core. And using our model, we looked at, does any variation in the material permeability affect the resulting composite behavior? And it turns out that basically the way that these magnetic composites work is that you basically, the magnetic material acts as a magnetic short. So it's so much higher permeability than the surrounding elastomer that it just locally shorts out regions of the, magnetically shorts certain regions of the elastomer. And then as a result, as long as the permeability is high enough, it ends up being dominated almost entirely by the shape. And so once it's above about 20 or so permeability, and in this case, both of our two materials have permeabilities up in the tens of thousands. Another inevitably trade-off in composite materials is that adding filler particles also results in a stiffer composite for two main reasons. The first of these is that the weighted average stiffness of the constituents is simply higher. You have some stiff material in the otherwise soft material. You also get additional effects that the particles limit the mobility of the polymer chains. You have more cross-linking sites. And so we found that for the higher loading fractions in the two materials, you ended up with a stiffness increasing by about a factor of 2 for the higher permeability composites. So we started with a composite about the same mechanical properties as human skin. We ended up with a material that had about a factor of 2 higher stiffness. So not ideal from our perspective. But based on this, we demonstrated the first stretchable magnetic core inductor using a liquid metal solenoid around a ferroelastomer core. and found that in both cases, we were able to get a sizable magnetic response. So about a factor of 3 increase in inductance. This means about a factor of 3 increase in the magnetic permeability of the material. We also found that because the platelets short out the elastomeric material more efficiently, you can get that factor of 3 increase at a lower weight concentration. So about 20% versus 80% for the more spherical material. You might ask why we don't then just increase the amount of magnetic material up to 80%. The reason is that it also has a bigger effect on the mechanical properties, the molding behavior. Essentially, 20% was the maximum we could effectively do for the material. However, because of this stiffness change, this was not very desirable for making a truly soft robot. And so we were interested in looking at whether there are ways to basically get that magnetic response without getting a resulting increase in stiffness. So working with a collaborator, Mike Bartlett, down at Virginia Tech, we looked at basically using more of a hybrid composite approach, combining magnetic liquid with magnetic particles into a soft elastomer. And so looking at a few different options, so the rigid particle composite would be similar to the ferroelastomer that I just talked about. The suspension composite has basically colloidal suspensions, and then the hybrid combines both effects. So we're trying to maintain our low mechanical stiffness, but still having a higher magnetic permeability. So in this case, we have our rigid composite looking at a variety of different particles: hematite, magnetite, iron, and sendust. Suspension composite, basically having suspensions of these particles into propylene glycol. And then finally hybrid, combining both. And as we'd expect, all three of the composites had very similar maximum strains. So again, up in about the 300 to 400% range. But the rigid particle composite had a significant increase in stiffness. The hybrid and suspension composites remain far, far softer. So we have gained, again, this benefit of being able to reduce the mechanical properties. And so the target in many of these cases tends to be about 100 kilopascals, which is approximately the stiffness of human skin. So we're often talking wearables for wearable devices or wearable robotics. And so we found that basically adding rigid particles stiffens the composite as we'd expect. Adding colloidal materials softens it. And so the big advantage of going this approach is that we can effectively tune the stiffness through the ratio of the colloidal to the rigid particulate. We're able to kind of get to kind of design in the resulting mechanical properties and able to gain higher permeability without losing mechanical compliance. Now, one of the challenges in soft robotics, and something I think that came up earlier today as well, was that soft robots are very good at gently grasping and conforming around fragile objects. However, soft materials are by their very nature soft. And as a result, they're not that good at imparting significant forces to these objects. So you can grasp it well, you can't always pick it up very effectively. And one of the things that we looked at was basically using stretchable magnetics to basically create large stiffness tuning in a fully soft structure for gripping objects. And so one of the challenges, so within what they call the magnetorheological elastomers, so this stiffness tuning elastomeric materials, basically there's a very strong tendency in this community to make the initial material very, very, very soft. So then you get a large tuning ratio. Basically, it's, you're able to get a lot of stiffening, but the reality is you might be going from extremely soft to very soft. You're not necessarily getting a significant useful actuator. You're just getting an eye-catching number. And so we looked at basically one of the advantages of this ability, this hybrid composite material, is we can tailor the mechanical properties for the desired behavior of the resulting composite. And it turns out, not too surprisingly, there's a trade-off between force levels and tuning ratio. If you have a slightly stiffer initial composite, you no longer get the 1,000% change in stiffness necessarily, but you now have something that can impart much larger force levels after stiffening. And so you're basically making a system that might be much more useful for actually creating a robotic gripper. In addition, these materials also can be used for direct actuation. So this video shows basically applying a magnetic field to a plug of the meteorological elastomer, and you're able to see a very fast response to the resulting magnetic field. So you can make a direct magnetic actuator that responds in a fraction of a second using this magnetoreological elastomer approach. And so the LED, the small light there, that's a Hall effect sensor that basically shows when the field has been turned on. Okay. And so using this approach, using this designed material, we created some magnetically tunable grippers that basically are able to conform when soft and then stiffen to actually grip the target. And so in this case, so the structure, what we're seeing here, we're seeing a gripper base, then a large electromagnetic coil, and then we're seeing then our magnetoreological elastomer around an air pocket that serves as the actual gripper in this particular case. And so we're then able to basically use this to then successfully grip things like fruit, things like soft objects without doing any particular damage. It conforms, grips it, able to pick it up, but then when you release the magnetic field, the gripper then softens and again releases the object. Okay. So in the next part of my talk, I'm going to be looking at more specifically using these materials to create basically pumps for trying to drive these soft robotic systems. And in general, there's been some work in things like soft and flexible pumps over the years, but generally they have paled in comparison to what you can do with something like a conventional electromagnetic pump. And one of the dominant electromagnetic pumps out there is something called a solenoid pump, where you have a solenoid, so a coil of wire that drives a permanent magnet piston back and forth. So it pulls fluid in and then pushes the fluid back out of a pumping chamber with check valves at the inlet and outlet used to derive directionality of the fluid flow. So again, it's a very common electromagnetic pump design, capable of high flow rates and pressures with the low applied voltage. So we thought, okay, this is a much more powerful technology than what we're doing in soft robotics. Can we make a soft version of this? So let's try to add flexibility to a solenoid pump. Basically we'll be printing this pump within a soft elastomer using, it's a type of a specialized SLA technology called the SLIPS process from a carbon 3D printer, where we're going to print the bulk of the material in this soft silicone and then create a solenoid based on, in this case, a thin gauge copper wire. So a flexible but not fully stretchable material. And then able to print one directional valves to then serve to control fluid flow and maintain consistent flow. And in this case, a collaboration with Dr. Rob Shepard, a professor at Cornell. And so the fabrication process, so using, again, this carbon 3D printer, first pumping the bulk of the pump in two pieces, then adding ball stoppers to then serve as our actual check valve, and then bonding these two halves together to create the actual soft pump body, after which we cure it to fully cure and kind of bond these two sides of the structure together. Next, we then create the center kind of piston, where we 3D print these elastomer coil guides that we then wrap this flexible solenoid. And then for this particular design, we have 7 distinct solenoids to allow us to drive the permanent magnet back and forth within the channel. We then place our permanent magnet into the channel and then bond it into the resulting chamber. So unlike the work that Ryan was showing, this is definitely, again, a little bit more of a manual process, a series of steps, and then assembly to create the final pump design. And then from this, so the resulting structure, we have, again, basically this design where we have the solenoids driving the piston back and forth. And then during the right stroke, it pulls liquid in from the top left and then out through the bottom right, then drives it back and goes through the opposite, basically the top right to the bottom left, to allow us to really use both phases of the motion to maximize the fluid flow. And again, a very common approach to making a solenoid pump. Now, there is one significant challenge in the design that I just presented, and that's that if we have a permanent magnet suspended in that channel, objects in fluid tend to settle to the bottom. They tend not to freely move back and forth to then pump the liquid. You get significant levels of friction. And so we decided, can we use magnetic materials to control this settling behavior? So if we're able to add a magnetic fluid, we can create a permanent magnet piston. So close to the piston, the magnetic fluid stiffens and forms a gasket around the permanent magnet. Further away, it serves more as a lubricant. So you're kind of gaining both a piston and a lubricant to create and something that we're calling magnetic fluid levitation. So it basically keeps it suspended in the channel, is able to then drive it back and forth to create the flow through the permanent magnet, through the solenoid pump. And to do this, so the colloidal suspensions that I talked about on the hybrid material, those were larger particles that tend to basically settle to the bottom of the fluid. But for something like the pump design, we instead want to have more of an equal suspension. So having the magnetic particles, say, suspended in the liquid. So we looked at an alternative magnetic fluid known as a ferrofluid, which is a nanoscale magnetic particles within a carrier liquid. This was originally developed as a magnetic propellant by NASA, that they were looking at having magnetic particles rearranged to propel spacecraft or to propel other different materials. But the big advantage of a ferrofluid is that because the magnetic particles are very, very small, they're able to maintain a uniform distribution. So you don't get settling, you get a nice uniform distribution of magnetic particles. And typically we do add a surfactant to minimize an agglomeration. So you don't want them to agglomerate into larger magnetic particles that'll then settle to the bottom. The work that I'm going to be showing here is just using a cheap educational grade ferrofluid called Ferrotech EFH1. That's just ferrite particles in a light mineral oil. So very, very common material that is relatively low cost. Using this, we developed a complete analytical model of the pumping behavior. And particularly, we're able to capture some really interesting behaviors that you actually get sort of almost like a snowplow type effect, where it tilts somewhat as it goes back and forth to the permanent magnet tilts somewhat as it goes back and forth through the channel. And we were able to model and kind of understand this and even confirm it. We actually went up to the Cornell Vet School and used their medical ultrasound to see the permanent magnet and kind of measure the permanent magnet going back and forth within the channel to kind of demonstrate that we had a good understanding of the magnetic piston within this pumping system. And so using this, we're able to demonstrate the first completely flexible solenoid pump. And because, again, this is a much more mature, much more kind of well-known pumping topology, we're able to get some very, very high flow rates than what we're seeing here. This is about 300 milliliters per minute flow rates between using the soft solenoid pump. And we're able to get reasonable efficiencies for a soft pump. So not as good as a copper base as a more conventional pump, but still up to about 15% efficiency using this flexible solenoid pump design. And then based on this, we then wanted to integrate this pump into more of a self-propelled boat or self-propelled kind of robot demonstrator. So using the Carbon 3D to integrate the flexible pump into the structure of the self-propelled boat, and then put it through a simple obstacle course to really show that going through a slightly narrower region, an upslope, and then out into to a basically just a pool at the end. And similar to what Michael had mentioned, these are tethered in the sense that we have electrical connections to them, but the propulsion and everything is simply built into the actual system to drive the device. And you could, in theory, start adding batteries and other things to make the power integrated as well. So this shows the actual robot in action, or the system in action. So squeezing through the narrowed region, and then starting to propel more quickly on the other side, going up the ramp, and then out into the final self-propelled trench at the end. So again, a very impressive demonstration of kind of self-propulsion. And so using this, we're able to demonstrate the highest flow rate for a flexible pump by an order of magnitude. And so able to get performance much more similar to what we were able to do with conventional electromagnetic pumps, conventional rigid pumping technologies. So able to generate significant levels of pressure, able to generate significant levels of flow by relying on techniques that are well established in traditional pump design. We wanted to kind of really build on this and look at making a more fully soft, more fully stretchable version. And to do this, we decided to look at really biology. And specifically, one of the most powerful creatures in the underwater world is the squid. And squid are capable of extremely fast propulsion despite a lack of structural stiffness. So almost entirely soft body, but they're able to propel themselves by up to 25 body lengths per second. So very, very quick. And they do this through a technique known as pulse jet propulsion. So the top or the head of basically the top structure in the squid basically expands to pull liquid in, and then rapidly propels that liquid out through a narrow nozzle to basically launch them forward and launch them at high speeds. And somewhat terrifyingly, apparently some species of squid can even launch themselves out of the water and propel themselves for dozens of meters in air as well. So so again, it's a very powerful technique in nature for propelling a soft creature. And people recognize this. So I'm not the first person to kind of look at making a robo squid. People understand that this is a very powerful way of making a fast underwater soft robot. However, this challenge of making a good soft pump has been a major limitation. That because current soft pumps have not been competitive with the natural solution, the examples that in the literature basically rely on a hybrid technique where some of the body might be soft to model after the squid, but generally you have rigid motors, rigid actuators embedded within the soft system. And so because of this, you're adding weight, you're adding significant limitations, and you're also giving up some of the advantages of having a fully soft robot, like being able to push through narrow holes. These end up being lost by going with this more hybrid solution. So we decided, can we use basically a fully soft electromagnetic actuator to drive something like a robo squid or a squid-like motion? And using actually the silicone tubing approach that Dr. Dickey had developed, we basically created a fine gauge, used this fine gauge, made a very soft electromagnet using just traditional wire winding approaches. So my student basically just took a drill and then basically wrapped the silicone tubing and was able to make up to about 150 turn liquid metal coil using this approach. And we characterized the force levels you can generate, and we're up in the hundreds of millinewtons for this 150 turn coil. So again, an impressive level of performance for a fully soft actuator. And using this, we then showed that we could use this liquid metal electromagnet to drive a permanent magnet structure to compress a water bulb to basically create a geyser of water, and demonstrate the ability to basically repeatedly fill and jet through that same nozzle within using this approach. And you can see the levels of current we're using again is something like 1 to 2 amps. So within that range that we can reliably use for extended periods underwater. So again, so a reasonable current level for extended use. And then we built our RoboSquat demo. So basically bought a fish tank from Petco and basically showed that we're able to propel this RoboSquid through the fish tank relatively quickly. So what's happening? We have a soft electromagnet on one end, we have a permanent magnet on the other, and we're repeatedly compressing that bubble to jet water and propel the squid through the water. Okay. So a lot of that work was more at the macro scale. But we're also interested, similar to Ryan, in looking at, can we apply these techniques to smaller medical robotics, smaller types of systems? Again, this is something we can draw on from nature, that hydraulic actuation in things like arachnid or spider leg joints are more efficient than muscle-based actuators at very small length scales. And so one example, the wolf spider uses internal hydraulic pressure to extend their leg joints. So they generate pressure in their head and thorax, and then drive their own hydraulic fluid to then move their legs. And notably, you're able to get very large displacement to body length ratios. But the challenge is that working with fluids at this particular length scale is very difficult. It's hard to push a liquid into a very small feature. And so working with colleagues both at Army Research Laboratory as well as Sarah Bergbreiter at the time here at University of Maryland, we looked at, can we develop a fully soft hydraulic actuator, and relying on, again, this 2-photon polymerization, so this nanoscribe type of printer that Ryan talked about, trying to 3D print at sub-micron resolution. So we're able to use a femtosecond laser to solidify individual voxels in photoresin and basically create very complex 3D structures at minimal additional cost per layer. And this is a very powerful approach that Ryan talked a little bit about, the cost of complexity for conventional approaches. Early in my career, I was more of a MEMS person, so clean room lithographic processing, where basically my advisor told me every additional mask step would add 1 year to my PhD. And then now we can, using these modern 3D printing approaches, we can create extremely complex structures out of things like photoresin in a few hours, a few minutes. So a very powerful approach to making microscale mechanical features. And so using this, we leverage the inherent properties of 2-photon to create fluid at them, or to basically capture fluid at the microscale. So 2-photon, the way that works is that you're using the laser to solidify basically material within a droplet of photoresist. And traditionally, you then you remove that resist. But if you deliberately basically create a bubble or create a structure that captures that resin, you can basically use that resin from the printing process itself as a hydraulic fluid. And so we're able to create a full bellows structure, several hundred microns on a side that we're then actuating using a DC needle probe. So we're basically pressing on the top bellows and moving fluid into the second bellows. And the big advantage that is, again, that complexity is basically for free. And so we can make very complex structures. We can easily print a second gripper right next to the first. And then we used one bellows to basically position an object within grippers and then closing grippers to grasp the target. So you're able to, again, just take advantage of this extreme ability to control features at the micro scale. And then more recently, we've been looking at kind of combining this approach to trying to add liquid metal into something like the bellows. So we can use electromagnetic actuation to basically replace the needle probe and have a more kind of self-actuated structure. So shows a 5 and a 3 turn coil using 2-photon polymerization that then we're injecting liquid metal to create our final inductor coil. So in conclusion, we're really looking toward building on this work to make a fully soft untethered robot based on a liquid metal solenoid pump. So trying to get, again, electrically controlled and significantly higher flow rates than past compliant pumps, and trying to leverage some of the work I've done in structural electronics to then integrate actuation, control, and energy storage. And so we're looking toward additive manufacturing, 3D printing to create high resolution and repeatable channels, and looking at other applications like wearable cooling, lab-on-a-chip systems on the body. And we're very interested in looking for partners and collaborators to help us kind of achieve these goals and kind of really push this technology forward. And I'd like to acknowledge everybody that kind of participated. Most of this was done back during my career at MRC Research Laboratory, a few people more recently at University of Delaware, as well as my collaborators at Cornell, Carnegie Mellon, Northeastern, and Virginia Tech. And I'd be happy to take any questions.